Okay, so this is the second video in your water quality section. We already covered the hydrosphere. This one's called water quality, or if you want, water pollution. So it's basically going to be covering this right here. So this is the biggest set of slides. This is the biggest chunk of the material that's, important that you're responsible for. Of course, you still need to know some stuff here and here, but this is representing a large section of this um, topic. So, when we think about dissolving a contaminant into water, a substance into water, we got to remind ourselves of a couple definitions, and that is solution, solvent, and solute. And the way to distinguish these simply is solute is the one of less amount. So if I dissolve sodium chloride into water, the solute is sodium chloride, the solvent is the water, the one that's in greater amount. And then your result is a solution. So the solution contains the solvent and the solute. And one of the things we like to say in chemistry is that like dissolves like. And what that means is that if a substance is polar, and I'll explain that to you in a second, it will dissolve in a polar solvent. Like dissolves like. If it's nonpolar, it'll dissolve in a nonpolar solvent. Okay? So when we think about classes of molecules, and this can apply to bonding too, we think about things that are what we call ionic, things like sodium chloride, because they hit a metal and a nonmetal. And then we think of things that are like nonpolar. Now, when we say nonpolar, we actually mean is that when the two atoms are bound together, the electrons in this bond are shared pretty evenly. So when you think about defining a pole, what do you think about poles if you think of North Pole, South Pole? You think of opposites. So in terms of things like molecules, we're thinking about opposite charges. So almost in a sense, sodium chloride would be the extreme example of polar, a complete full separation of charge with a plus and a negative. And then this, since these are two exactly the same atoms, the idea here is which of these two likes the electrons more? And obviously, since they're exactly the same, they're going to share them perfectly. This would be the example of the extreme, other end of the extreme, nonpolar. But what we typically have is when two atoms bind together, one of them likes electrons more than the other typically. And it pulls these electrons in this bond closer to itself. And then what you wind up is kind of like what we say is a partial negative charge. It's the symbol we use, but you don't have to worry about that. It's not as extreme as this. So you have some sort of charge separation. This is what we call polar. Well, it's a difficult concept to grasp, especially for non-science majors. So I've come up with an idea of just kind of helping you get around this a little bit and giving you something to look for. What I always tell students is, first of all, water is polar. Okay, this is the structure of the water molecule. It is actually bent. We know that. It's got a couple electron pairs up here. Oxygen likes electrons, so we wind up with this type of situation where it does have a pull of electrons in these bonds towards the oxygen up here, resulting in this what we call partial negative charge. You don't have to worry about this pull of electrons, how you figure it out, how do you symbolize it. Just accept the fact that water is polar. Okay, and it is bent, and it's bent because of those electron pairs up there. Now, for something to dissolve in water, it also needs to be polar. And what I've come up with is ways for you to think about looking for pieces of water within the molecule to decide whether it will dissolve in water. So, for instance, this is polar also. It dissolves in water also. Why? It has a piece of water. OH. You're looking for OHs. That is the best thing that makes it the most soluble. If you don't have OHs, you're going to want to look for O's also. And you could have things like this. No OH. This is defined like this. You have a hydrogen here, double bonded here. So there is no OH group. So this will be somewhat soluble in water, but not as soluble as something like this that has that OH group. So if something doesn't have any pieces of water, let's say a hydrocarbon. So we've talked about hydrocarbons a lot in this semester. And if you take something like this, this is butane. Do you see pieces of water? No, there's no OH, no OHs. Not only that, there's no O's. So hydrocarbons, or oil, if you will, we've studied oil, right? And hydrocarbons, oil and water don't mix. Why? Hydrocarbons are not polar, water is polar. So different hydrocarbons will be soluble in each other, but they won't be soluble in water. And water won't be soluble in a hydrocarbon. So that's all I want you to get out of this really is looking for this. It at least gives you some idea. Now, you might say, well, this doesn't have pieces of water. Well, if it's ionic, then we ignore that. We say, okay, this has full charges and this will dissolve in water. So a lot of our salts will dissolve in water. But if you look at things like sugars and stuff, you'll find these OH groups on them. And we know that sugar is very soluble in water. So you're looking for one of two things: ionic compound that has a metal and a nonmetal, and also pieces of water. Now, these are just guidelines. They don't hold exclusively because there are ionic compounds in which the bonding is so strong they do not come apart in water and therefore not very soluble. And I just want you to be aware of that. Okay, so we talk about water pollution then, and I've given you some pages in your chapter there to look at this. There's one thing we define as point and non-point source pollution. And when we say point, it's kind of exactly what it says. It has a direct source. The classic example of that is an end of a pipe. You see a pipe discharging waste into a stream. That would be a direct discharge or a point source of pollution. Non-point is something that's not as easy to identify, and it doesn't come from a single point. So you could think about like a golf course. Excuse me. It doesn't come from a single point. It's all along. If you go to the golf course there, Old Fort, there's a whole area that's along Stones River. And if you're putting down, chemicals for weeds or insects or fertilizer and stuff, that can run right into the river, and that's considered non-point source pollution. So the classic example is agricultural runoff is non-point source pollution. Don't worry about this. Sources, you can think of all sources of pollutants. They're listed in your book, things like that, industrial discharge, factories, petroleum mining, all sorts of sources of pollution, of course, solid waste. Okay, now when we think about water quality regulations, it depends on what you're using the water for. So it's not necessarily defined based on the purity of the water, based on the suitability for different intended uses. So if you will, nitrate in domestic water that's delivered to your tap at 10 milligrams per liter versus, what's going on in an agricultural field, this is dangerous, and you want that's a max concentration. But in agriculture, nitrate is useful for plants, and we don't care about it if it's above 10 milligrams per liter. So it's important to realize that EPA sets standards based on different things, and they do have drinking water standards. And they have something called MCLs. That stands for maximum contaminant levels, and maximum contaminant level goals. That's a C there. So this is just adding a G, meaning goals. These here, the maximum contaminant levels, are enforceable. This is ones that they actually enforce. These are not enforceable, they're just goals. So what we see here is some MCLs for different substances. If you look at lead here, lead's pretty famous. It's 0.015. This is milligrams per liter, which is the same thing as a part per million. You might see some tables in parts per billion. Then this would be 1, 2, 3 places over. This would be 15 parts per billion. So you see different MCLs. These are enforceable. If you're running a water treatment plant, if you're discharging liquids, you have to meet these standards. An MCLG is not enforceable, but what we often have is things like carcinogens. Just by the nature of what they are, we typically set these with MCLGs equal to 0. Now, that can't be attained. That's one of the key things to realize. You can't ever prove there's 0 amount in the water. All you can do is test it and it's as good as sensitive as your test, right? So you might say, well, my test can test down to 1 part per trillion. It's super sensitive. So if I don't detect the lead, it doesn't mean there's no lead there. You might have zero point 0.1 part per trillion in there. I can never prove. That's why these aren't enforceable, MCLGs, because they're often set at 0 for especially carcinogens. In fact, they're the only ones that set at 0, I believe, as carcinogens. But they're not enforceable, and sometimes we just don't have the technology to test or to even get the levels down that low. So it's important to realize that distinction. Here we have types of water pollutants. What I have here is a graph of crop yield versus fertilizer addition. And there's 3 regions I want to point out. This here would be no fertilizer, of course. This would be 0 here, right? This would be the amount of fertilizer that's optimum. Did you get the best yield? And down here now, you're getting some sort of toxic effect, right? So, and these are just the way in which some of these fertilizers are added, the forms they're in. But when we talk about these nutrient fertilizers, we're talking about nitrogen, phosphorus, and potassium. Those are the major nutrients we add to our agricultural fields. I just want to remind you of the nitrogen cycle. It's one of those things where I told you where this, your next exam is not cumulative, but there is material that you need to be familiar with. So go back and review the nitrogen cycle. The environmental concerns with nitrogen is, firstly, it's poorly held in soil. It's very polar, if you will. It can absorb, because you've got those oxygens, but you also have that charge there, right? So this dissolves very easily in water, highly soluble. And in drinking water, it's a problem because in infants, they have a different stomach bacterial microflora than full adults do. I think it's like 6 months and less. And what happens is in their stomach, they convert nitrate to nitrite. This attacks hemoglobin. The iron can no longer bond the oxygen. So effectively, the nitrite is keeping the oxygen from binding the hemoglobin. Hemoglobin, of course, is that component of your blood that transports the oxygen. You get blue baby syndrome or methemoglobin anemia, which is the medical term, but blue baby syndrome. The baby actually will suffocate if the problem is not solved, and that is they're not getting oxygen. The other concern with nitrogen, the other major concern, is that in the environment, it's typically often a limiting nutrient. That is, plants don't grow uncontrollably in the environment because typically they don't have enough nitrogen, and phosphorus is the other big one. In fact, most people would say phosphorus is more important. But these two, nitrogen and phosphorus, keep plants from growing uncontrollably, and those plants include algae. So what happens if you get runoff into water that contains nitrogen and phosphorus, all of a sudden the algae can grow like crazy because those are the things that were keeping them from having enough nutrients to grow. Everything else they pretty much have, carbon, things like that, water. They grow uncontrollably, and since they're microscopic organisms, they don't have long lifespans, and they die. When they die, the bacteria love them as food, and they carry out respiration, as always. And you all know what respiration is. You have a carbon source. They use up oxygen. You form CO2, right? And if it's CH carbon source, you get CO2 plus H2O, of course. That's your basic respiration. It's also the same as a combustion reaction, right? Just no heat. We have enzymes that speed it up and carry out those reactions. Well, that's going to consume up all your oxygen. That's what happens. The lake winds up getting depleted of oxygen. So the presence of the nitrate causes the algal bloom. The algae die. The bacteria eat the algae and consume oxygen in respiration. And you get things that look like this. This is a big problem in numerous areas across the country, in the Mississippi, where the Mississippi empties into the Gulf, Chesapeake Bay region, the whole Gulf region down south is affected by this. Another important pollutant is sewage. Just raw sewage. Now we treat our sewage obviously when you flush your toilet or run your garbage disposal and your sinks and all of that. It goes to a treatment plant where it's treated, and they have to degrade the organic loading down to a certain amount. So what happens is, when, just like we talked about before, anytime you get organic material in the water, here was my example here, the organic material happened to be algae, You carry out respiration. Well, if you were to dump your sewage into the river without treating it, all that raw sewage, bacteria would love it. They'd carry out respiration, and you deplete your oxygen. So most organic materials are biodegradable. That's what you see as an oxygen sag curve. So here's my system that's happy with all the best fish, and you've got clams and all of that. Then we have an organic loading, and what happens is the bacteria start to degrade it. So my oxygen levels, this is the y-axis, this is distance downstream or time, oxygen levels start to decrease. We get decomposition. Then you get to the point where the oxygen levels are so low that any organic material that's remaining must be degraded anaerobically without the use of oxygen. Once it's all degraded, then the water will start to recover. We reoxygenate from the surface, from plants carrying out photosynthesis. These are actually worms down here too, I think. And then eventually it returns to normal. How long that takes and how far downstream will depend on the amount of waste that's added and the amount of oxygen that's in the water to start with. The other thing I want to point out is that oxygen solubility, it depends on both temperature and altitude. The one I really want to focus on is temperature. These are two different altitudes. So this is sea level here, and you see at 25 degrees C, it's about 8 point something, right? 20 degrees C, it's about 9, right? And it changes with temperature. As I said to you the other day, I think in a video or maybe in our Zoom meeting, gases' solubility decreases with increasing temperature, and that's what you see for oxygen here. So in warmer water, the oxygen gas molecules have more energy, and it's easier for them to escape the water, and that's why this happens. It's the reverse of what we expect when we dissolve solids. As I mentioned, a solid will dissolve easier in warm water than it will cold water. When you dissolve your sugar in tea, it dissolves better in warm tea than cold tea. This is just showing at a higher altitude, the amount of oxygen is less. And that's because of what we talked about with the structure of the atmosphere. As you get higher up into the atmosphere, the air's thinner. The pressure's less. If the pressure's less, the air's thinner, that means there's less oxygen also. So by nature, you're going to have less oxygen in a mountain lake than you will a surface lake. The actual movement of oxygen in water is slow. So if you have a lake, here's those terms in the thermal stratification we talked about. If you have a lake, you have your epilimnion up here, right? And here's your thermocline. It takes a long time for oxygen to move down here. That's why those fall and spring turnovers are key. So we define this biochemical oxygen demand as the amount of oxygen consumed during microbial utilization of organics. So at wastewater treatment plants and water treatment plants, they actually do tests, what are called jar tests. They'll take a sample of their wastewater, right? And then they'll expose it to bacteria and see how much oxygen they consume in degrading it. And that tells them what their biochemical oxygen demand is. And EPA will require them to get, below a certain level. And this is just showing you kind of the oxygen sag curve. Once again, not the greatest coloring here, but this is the oxygen sag curve here. And then this is what the BOD is here. So as the BOD decreases, the oxygen will recover. So as it's being degraded, the oxygen is depleting. Once it's come to kind of normal levels or background levels, the water's oxygen level can return. The last parts of this video are metals and organics, and I'm going to go through these pretty quickly, especially the metals. Metals I just want to mention because there's some information in your slides, in your book. These are common metals that are, not toxic. They are, pretty much nutrient metals. These are some of your common toxic ones. That's mercury, lead, cadmium, chromium, and arsenic. And I go through the slides and I give you some information on them. It's not something I'm going to ask you to regurgitate in an exam. It just tells you like sources, concerns, and then things like the chemistry. What I mean by the chemistry is which form is most important. And when you see mercury, you'll see it's like the organic forms like methyl mercury like this and dimethyl mercury. These are the ones that you get your tuna fish warnings on. That's what they're really about, methyl mercury, not the element mercury or even mercury 2+. So that's what that chemistry section is as you go through the slides. Solids, we measure them as total suspended and the ones that are dissolved. The dissolved will include your salts and minerals. The ones that we consider not dissolved, suspended, we basically do a filtering test. And if the particles are bigger than 0.45 micrometers, we consider them suspended. If they're less than that, we consider them dissolved. And that's just to give you an idea. Fresh water contains anywhere from 0 to 1,000 milligrams per liter of the total dissolved solids. Now, organic contaminants, there's all different sorts of them, of course. There's solvents, petroleum, pharmaceuticals, pesticides, personal care products, food additives, etc., etc., etc. I wanted to focus on a couple important pesticides. These are ones that have been banned in the United States. They all have the same general structure as you notice. No pieces of water, so they're not soluble in water, and a bunch of halogens, all being chlorines. These were the early pesticides that caused a lot of problems, which led to, Silent Spring by Rachel Carson, the formation of the EPA, and the outlawing of a lot of these chemicals because they were collecting in our birds of prey, like the bald eagle. The DDT became the poster child for this, the infamous one, but it was all these types of compounds. But DDT was persistent, bioaccumulated in the food chain, and was toxic. It interfered with calcium metabolism that resulted in eggshell thinning. It was not designed to do that. It's designed as a neurotoxin. That's the way it works. It affects the insect's nervous system. I'll show you that in a second. But a lot of these chemicals in the environment have side effects. They affect different things in our body that we would never have predicted based on their normal chemistry. And that's what happened with DDT. So we came up with things like organophosphates to replace a lot of those organochlorines. These are organochlorines because they weren't as persistent. But turns out they're actually more acutely toxic. So they're more dangerous for the people working with them, the people in the factories making them, the farmers using them. But they're less toxic. They're less long-term in the environment, sticking around. They'll break down easier in the sunshine, in the water. But they are more acutely toxic. If you have a spill in the environment, these things are worse because they're much more toxic. This is a very common one. And this is the way a lot of these nerve toxins work. So here's your two nerve cells, and we know that we have a synaptic gap here. This is blown up. Neurotransmitter moves across that synaptic gap from the end of one cell to the beginning of another, if you will. It's these dendrites on the end. The neurotransmitter is sent across, leaving from here, and it fits into these little sites, and that sends the signal, continues the signal. Well, acetylcholine is the neurotransmitter, and it's typically broken down when it collects in here by the enzyme. Anytime it ends with ASE, that's usually an enzyme. And it breaks it down so it doesn't collect too much. Well, what these insecticides do, they keep this from breaking this down. So in the insect you're trying to kill, this stuff keeps accumulating. That results in an uncontrolled response. The insect basically has a, just system just totally shuts down because it's just overstimulated and basically paralysis and death ultimately. So these chemicals, a lot of them you'll see, especially the organochlorines, not the organophosphates. This is the way organophosphates work, by the way. This right here really is them. And DDT works similarly, just a little bit differently. They all have slightly different mechanisms. These stands for persistent organic pollutants, and these are the ones. A lot of those organochlorines that have been banned, and here's their use. And this is a worldwide list basically of 12 POPs known as the Dirty Dozen. They're mostly insecticides, as you see, or some sort of pesticide, I should say. Some are fungicides, but most of them are insecticides. And there's a few others that are not insecticides or industrial, and some that are not produced intentionally or produced in combustion reactions. This shows you the structure of some of these pesticides and some other things we've been talking about, these organochlorine type compounds. There's DDT up there. This is famous, the biphenyl ring, the PCBs. These are used as transformers right here. Electrical transformers, things like that. They've been phased out also. And this is what EPA uses to classify these compounds. This is the last slide here. It's just showing you what we consider persistent or highly persistent. And there's differences between water, soil, and air. Air is pretty much just measured on a 2-day factor, but all the others are on month factors here, and you can see if it's less than 2 months, greater than 2 months, and greater than 6 months. And if they stick around a long time, that's where you get this bioaccumulation and biomagnification that we talked about before. And that ends this video.